Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're back, and next we'll hear about from Sebastian Bubeck, who is based right here, about the influence of the seed in random recursive graphs and trees.
Yes, thanks, Yoval. Okay, so this is going to be a fairly simple talk in the sense that I will talk about probably the simplest possible model of a random evolving graph, and I'm going to ask possibly the simplest non-trivial question about it. And we will see that the answer will be not so simple. Okay, so the star of this talk is going to be this object, UAN. So n is an integer. UN is going to be a tree on n vertices that I define as follows. So this is a tree, a random tree on n vertices. And I define it by induction like that. UA1 is just a single node, the unique tree on one node. And UAN plus 1, so UA stands for uniform attachment, so I have UAN here. And then I'm going to add a new vertex n plus 1. And n plus 1 is going to attach to an already existing vertex, which is chosen uniformly at random. Okay, so it just sends an edge like this to a vertex chosen uniformly at random. Okay. Now the question, so that's the model we are going to look at. And the question that I want to ask is the following. Imagine that you observe a snapshot of this random network at a certain time k. Okay, so observe a snapshot at time k. Okay, meaning that you observe UAK. The question that I want to ask is, does this give you any information about the future evolution of the tree? Okay, so does this give information about UAN as n goes to infinity? Okay. So maybe I'm going to state this a little bit more formally, but it seems like the information that I obtained at time k is going to decay as n goes to infinity, and I'm going to be interested to see how fast it decays and things like that. That would be the natural thing to do, but we will show a more surprising result, which is that this information at a finite time k gives information about UAN for any time step, even at infinity. So more precisely, what I want to do is that I have UAN, and I condition on UAK being a certain tree. Okay, so I want to look at the conditional distribution of UAN given that at time k it was a certain tree S. Okay, and I want to know, does this depend on S or not? So there are only a finite number of trees on k vertices. So what I'm going to look at is I'm going to look at two of these points, okay, two trees on k vertices, let's say S and T, and I want to know, are the two distribution UAN condition on UAK equals S and UAN conditioned on UAK equals T, do this distribution in the limit become the same form, or do they stay different? So in other words, I will look at the total variation distance between these two objects. And I want to know what is the limit as n goes to infinity. Okay? So if this is strictly positive, it means that observing a snapshot at time k at any finite time gives me a lot of information about the future evolution of the tree. Okay. And the theorem that we will prove, or that I will tell you a little bit about how we can prove this theorem, is that this limit is always strictly positive. Okay, so let's call that delta of S and T. By definition is this thing. And the theorem that we proved, so it's myself, Ronan Eldan, who still is, I don't know, a postdoc here, Elhanan Mossel, and Mickey Ratz, who was with a graduate student. Elhanan is his advisor, and he was my intern. So we proved that for any S not equal to T, delta ST is strictly positive. Not equal, of course, means non-isomorphic. Okay? To have two trees non-isomorphic, I need K to be at least 4. Okay, so that's the theorem.
And also in your total variation, it's just up to isomorphism, right?
Yeah, of course. So
Otherwise it would be.
Yeah. This a tree on n vertices, it's an isomorphism class, right? So it's of course up to isomorphism. Okay, so I could have asked the question, do you think this limit is going to be 0 or not? And the natural answer should be yes, the limit of course is going to be 0. I don't want to ask this question, but let's see why, how come this could be possibly true. Okay, so I'm going to show you why this could be possibly true. So let me give you an example, which is going to use heavy machinery already to prove that even in this case it's strictly positive. So let's say that S is a star on K vertices. Okay, so it's something like that. Okay, so that's a star on K vertices. And T is a long path. Okay, it's a path on K vertices. Like that. Okay, so why observing this or that gives me information about the future? Well, it's going to give me information about the future because the diameter will behave differently if K is large enough. So let me tell you two facts about the diameter in uniform attachment trees. So fact 1, it turns out that the diameter of a UAN, this is asymptotically as n goes to infinity, almost surely equivalent to E log n. Okay, so this was proven by Pittel in '94. So actually the proof, even though it was not, the result was not explicitly written, already appears in result of de Vroy in the 80s. So that's the first fact. Okay, so the diameter is this. But here is the really crazy one. Very, very impressive. So if you look at the variance of the diameter, this is O of 1. Okay, so despite uniform attachment being this completely random process, right, the diameter is very tightly concentrated. It's basically E log n plus a constant. Okay, actually it's not entirely true. It's E log n plus a constant log n plus this variance term. Okay, and this was proven by Adario Berry and Reed in 2009. Okay, and this was open for a very, very long time. It was first proven that it was O of log n, then O of square root log n, log n, square root log n, and finally O of 1. Okay, so this is really non-trivial. So now let's see how we can use these two facts to see that on this example, the total variation in the limit remains bounded away from 0. All right, so I want to look at the diameter of UAN conditioned on UAK is a star. And sorry, I wrote things for the diameter, but these results are for the heights. They are also true for the diameter with a 2, but let's use. So this is the height. Okay, so there is a natural, you have to specify, you have to fix the root at the beginning. All right, so the diameter of UAN given that UAK is a star. Well, this is bounded by. The root is the first vertex in those two results, okay? But note that in my description there is no root, okay? When I hand you a tree, you don't see a root somewhere, okay? There is no root. But these results are when you say, okay, I specify a root. So let's see what is this diameter. Well, here is the picture, right? You started with this, and now everybody is going to grow, right? Like that. The diameter, of course, is at most, the diameter in a tree is at most twice the height, okay? And here the height is going to be bounded by E log n plus a constant. So the diameter is going to be bounded by 2E log n plus some constant with high probability. And the plus constant is because of this result. Okay, good. All right, so that's clear. Now let's look at the diameter of UAN when UAK is a pass. Okay, so you started with this. And you have grown trees here, everywhere. Of course, these trees, right, if I just look at them, their distribution condition on their size are the same of uniform attachment given that size, right? So now, here you can see that the diameter is going to be larger than I can take the height of this one plus k plus the height of this one. Okay, so it's going to be larger than k plus, okay, how many vertices will I have here? Well, with reasonable probability, I will have at least n over k, okay, in this. So it's going to be at least the diameter k plus 2e log n over k minus the constant of the variance not with high probability, but with, let's say, with reasonable probability. Okay. All right, so now you see that the diameter on this one is going to be larger than this one as long as k is larger than this constant, where this constant is just a universal constant that depends on the variance of this. So we see that when k is large enough, I can tell, if you want, given an observation which is a large tree, I can tell you if you started with that, with S or with T, because I can look at the diameter. If the diameter is large enough, I will say, okay, you started with this one. That was in the past.
For that assertion, you don't need higher moments. I mean, it's not necessary. It's okay to just tell the variance.
Yeah, you can just do
measure zero set that they differ on, or not.
So here you can just do Chebyshev, right, and have a certain constant that depends on the variance, and this will happen with probability at least 0.9, right, or 0.99, and then you need this one to be a little bit larger than 0.01. Okay. So this is fine.
So it seems that the way you described it, it doesn't quite seem to follow from these two facts. Like,
okay.
Fact one just says it's
absolutely
log n times 1 plus little o.
Yeah, you're totally right. So the truth, but sometimes you have to lie a little bit, is that there is plus some constant, let's call it b, log n.
In both places.
Yeah, in both places, with the same b. And this indeed does not follow from this. But it is true.
So that when you plug in the n over k, it still works.
It still does work, yes. Absolutely. That's true. That's right. Okay, good. So we see that in these two examples, the theorem is true. Now, this is very fragile, right? I mean, I needed this path to be very long, and I'm comparing to a star. Okay. Of course, if I compare even a very long path to a very long path where I have added, right? If I add somebody here, or if I add somebody there, this proof technique is not going to work. The diameter will be the same essentially. So you need to go beyond diameter to see the difference in the limiting trees. So now I will tell you how we prove it in general. Okay, so the general proof. I won't have time to give you the intuition of where it comes from, but I can tell you offline if you want, and then I will conclude with some open problems. But I want to tell you the general proof because there is a statistic that can distinguish the seed. Okay. Another point of view is that you want to know what is this seed S. Okay. All right. So the general proof is going to go as follows. So I need some definition. I'm first going to define a decorated tree. Okay, so a decorated tree, tau underscore, like that. It's a tree together with a decoration. Okay, and what is a decoration? A decoration, it's a labeling of the vertices. Okay, so L, it goes from tau to the integers. And the way we are going to think about this labeling is that you put arrows on a tree. Okay, so imagine that tau is this. Okay, let's say this is tau. Now the decoration is going to be a certain number of arrows on each node. Okay, so maybe I have 2 arrows here, 1 arrow there, and 1 arrow there. Okay, so that's a decorated tree. Next, I'm going to define a decorated embedding. of a decorated tree into another tree. Okay, so I have a decorated tree, I have another big tree, and I'm going to define a decorated embedding, which is going to be a certain way to embed this decorated tree into my bigger tree. So a decorated embedding, let's call it phi bar. So phi bar is going to be defined as follows. So I have my tree, T. Okay, it continues here, it continues there, it continues there. Okay, so this is T. All right. My decorated embedding, the first thing that I need to do is that I need to embed tau into this big tree. So here in the way I drew it, it's obvious that I have embedded tau right here. Okay, so tau is right there. Now I need to embed the decoration. I need to embed the arrows. So I had 2 arrows there. What I'm going to do is that I'm going to choose 2 vertices in that subtree, and I'm going to put the arrow there. Okay, so I need to choose 2 vertices here, and I put the arrow there. Here I have just 1 arrow, so I need to choose 1 vertex in that subtree. I put the arrow there, and here I had also 1 arrow, and I put the arrow there. Okay, so this is a decorated embedding. I embed the tree, and then I embed the arrows. Okay, I took the arrow and I embed that in the corresponding subtrees. All right. Next, I'm going to define f tau bar of t, which is simply the number of decorated embedding of tau bar into t. Okay, so this is the number of these guys. Okay, number of decorated embedding of tau bar into t. All right. Now, the key observation is the following. The key technical observation is the following. The expectation of f tau bar into a UAN. If I look at the number of decorated embedding of a certain decorated tree into UAN, can be expressed as a function of the expectation of f tau bar prime of UAN minus 1 for tau bar prime, which is smaller in a certain sense than tau bar. Okay. So again, I can express this thing, okay, the number of decorated embedding. I have a recurrence formula as a function of the same expression, the number of decorated embedding, but for smaller subtrees. So what is this smaller? It means that the size of tau prime is smaller or equal than the size of tau, and the weight of tau prime is smaller than the weight of tau, whereas the weight is just the sum of the labels. So the total number of arrows that I have in tau prime is smaller than the total number of arrows that I have in tau. Okay, so this is very, very easy to do. Okay, this is just a few lines, you just need to work a little bit. So now, what does it mean? It means that I can find the martingale in the span of those things. So in the span of the f of this statistic, so this statistic, of course, I can compute them. Given a big tree, I can compute the number of decorated embedding of a certain decorated tree into tau. And now, because of this key observation, I just said that in the span of this thing, so in the span of the f tau prime of UAM, the linear span, when t prime is smaller than t, I have a martingale, okay, just because of that. Now the key will be to show that I can find martingales like that which are bounded in L2. Okay, so they will have a bounded variance, and because they are martingale, and of course at the beginning they are different. Okay, if I look at the number of decorated embedding of S into S, it's different from the number of decorated embedding of S into T, which is 0. I cannot embed S into T. So I know that they are different at the beginning. They are martingales, they will stay the same in expectation, and I have to show that they are bounded in L2, and then that will allow me to distinguish in the limit. Okay, so this is the proof. Now I want to say, just the open problems and something about references. So this proof technique was not invented by us. It was invented by Nicolas Curien and his co-author. So Curien, Thomas Duquesne, so a bunch of French people, Korczemski, and Manolescu. Yeah, but they are French. So that was a few months ago, and they invented this proof technique to solve an open problem that we had in my work with Elhanan and Miki from before, where we asked, so what we did is that we asked the same question, but in the preferential attachment model. So in the preferential attachment model, it's the same description, but when somebody comes in, it connects with somebody chosen at random, but with probability proportional to the degrees. So if somebody has high degrees, then we are going to be more likely to connect to him. What we proved is that this theorem was true if S and T have different degree distributions. Okay, and the way we did it was sort of similar to the diameter, but for the preferential attachment, meaning that we looked at the max degree. And then these guys came in and they did this, except that it was different in the sense that their notion of decorated embedding is local. So it's the same thing, except that the arrows, instead of putting them in the subtree, you have to put them in corner around the vertex. So a vertex that has a degree like this, right? It goes like this. And in what Curien et al. Did is that the arrows, they embed them in this corner, like this. Okay. So in some sense, their embedding is local. You embed the tree, and then you embed the arrows locally around the tree. In our case, the embedding is non-local, and so it's more complicated to show that these martingales are bounded in L2. But the proof scheme, in any case, was developed by those guys. Now, open problems. So let me define delta alpha between S and T, where it's the same thing, except that now the model that we look at is that somebody comes into the network, is going to connect with probability proportional to the degree to the alpha. Okay. So uniform attachment is alpha equals 0. Okay, degree to the 0 is 1. So you connect independently of the degrees. Preferential attachment is alpha equals 1. So now we know that this theorem is true. Delta alpha ST is always strictly positive if alpha is 0 or if alpha is 1. What about other values of alpha? Okay, we don't know. This is open. And maybe even more interesting is what can be said about this function. Alpha gives delta alpha of ST. Is it monotone? Convex? I don't know. Okay, so is it easier to see the, so is the influence of the seed stronger in the preferential attachment model or stronger in the uniform attachment model? Trivially, one would say that it's stronger in preferential attachment, but it's not so obvious. So we have zero idea on how to attack this question. All right, I will conclude here. Thanks.
Question?
Yes?
One very simple question. As k goes to infinity, which is the size of the small piece, does delta go to 1?
That's an excellent question. So in this case, the answer is yes. Mm-hmm. Okay, and that can be seen by those calculations. Uh-huh. In general, we don't know, of course, but let me tell you one more open question since you asked this. Let's say T is this, okay, it's a pass, like that. And S is pass like this, except that at the end, you have a little fork like that. So I wanted to ask how fast does the TV between those two things go to 0 as k goes to infinity? Okay, but it's not. The more I think about it, the more I think that even as k goes to infinity, the TV stays bounded away from 0 between these two things. Which
I mean, I was even wondering whether it goes to 1.
1? No.
Why not?
No. No, I cannot believe that. No, it's.
No, it's not. It doesn't go to 1 because right away there's some positive probability of coupling.
No, there is more.
But it goes to 0.
That's exactly the point. As k goes to infinity, those local effects seem to go to 0.
No, between these two, it cannot go to 1. Why not?
Wait till the first time that you touch the right-hand side. I mean, with positive probability.
Yeah, I think this is true.
Yeah, okay.
I think this is true. You can couple them.
Okay, fine. Okay.
But it could be that it remains strictly positive. And this type of question will have to go way beyond this, because this is nice just because of this observation, which makes all the calculation tractable. But this is very weak. I mean, it's not at all the best statistical procedure. It's not even really a statistical procedure. So, yes.
Also, what's the problem with their embedding in your?
Oh, their embedding would absolutely not work. So, because it's local, it's telling you something about the degrees. And the degrees in uniform attachment, they are all over the place. They tell you nothing about what was at the beginning. So in uniform attachment, the key new insight that we have is that in uniform attachment, you need to look at subtrees instead of looking at degrees, that's it.
You got to look at total variation at this time, right? So
Yeah. So we looked at, in this paper, we also looked at weak limits. So weak limits mean in the Benjamin-Isham sense, but in that case, it's obvious that this always goes to 0 because you only make a difference locally.
I think
So this is a joint work with Ning Chen and Pinyan Lu from MSR in Asia, and Ning is from Nanyang Technological University in Singapore. So in this talk, I will argue why we should be doing competitive analysis against a variety of benchmarks as opposed to doing it with respect to individual benchmarks. So, so in the competitive analysis, like from a high level point of view, what we have? We need to give an algorithm that for some objective maximizes this objective for any input. And the integral part of any problem within competitive analysis is a benchmark. So, and what is a benchmark? It's basically describes the desired outcome, which is usually specific to a problem. So if you have a problem, then usually this benchmark is something like optimal solution for a given input and given objective. And normally what we do, we minimize competitive ratio, which is the worst case ratio of the benchmark over the algorithm. And normally we think of algorithm being handicapped compared to the benchmark by handicapped, well, some examples are like online algorithms. So you should do something online where benchmark is offline, or I don't know, actually you can do it for mechanisms in algorithmic game theory where the mechanism must be truthful and the benchmark is something that doesn't need to be truthful, or algorithm must be computationally efficient in approximation algorithms, and F is just like arbitrary thing. It doesn't need to be computationally efficient. But like here, the important and really integral part of the competitive analysis paradigm is a benchmark. And as I said here, well, usually the benchmark is fixed, and we never think about changing it. So it's like we have a problem, the benchmark is given, and here it is. But actually, sometimes, but this is quite rare occasions, people look at variants of benchmarks. So different variants of desired outcomes. So for example, you might have different objectives. Like in AGT, we have this social welfare or revenue, and then the outcome you will be wishing to achieve is different. So this happens sometimes. So people consider more than one benchmark. Well, even more rare, people actually do like a family of benchmarks. You may consider like a family of well-structured functions, maybe single parameter, maybe like n parameters, but some not very wild family. I probably have seen like a couple of papers on this, but by and large, people do it very rarely. And actually, I never seen results of the following form, where we look at very abstract problem, like give me any benchmark, or maybe benchmark from very broad class of functions, and tell me something, what would be your competitive ratio with respect to this abstract function. So actually never seen a paper of this form. Maybe there are some, but I know nothing. And in this talk, I will try to convince you why this kind of question deserves much more attention than we are paying to it. So to give you some context, I will be talking about this very nice setting of digital good auctions and some close relatives of it. So in this setting, we have one seller, we have n buyers, and we have just one good for sale. And let's say it's a digital good, like this CD. And we can make as many copies as we like. So we have essentially unlimited supply here. And buyers, they have some private values for a single copy of the item. They just want one copy. So they, this is called unit demand. And here, what we are willing to achieve is some kind of truthful auction. So we assume that these buyers, they submit bids in a sealed envelopes, and then the seller decides on who gets the item and how much they pay, and he want to ensure that it will be of the best interest of buyers to report truthfully, to tell their true values. So this is kind of a restriction on the algorithm or auction here. And as a seller, we want to maximize our revenue, so how much buyers pay to us. And as we are in this worst case analysis paradigm, we want to compare to some benchmark. So this is essentially unlimited supply setting, so very simple. So you can imagine doing some kind of variations of it. For example, if we have a limited amount of resources, let's say 2 items, or like some limited amount, less than number of buyers. So this setting is called limited supply. You can also imagine doing something online here. Like, let's say we return back to this unlimited supply case where we can make as many copies as we want. But now buyers arrive online, so they do not come all together. They come sequentially, one by one, in a random order. And then we need to decide on the location and payments right away once they arrive. So for example, the first guy arrives, we give him an item, charge payment. The second guy arrives, and so on and so forth. OK, forget about online auctions. You can also consider some more generalizations and variants of this problem. So for example, maybe you cannot serve them for sure, but you can serve them with certain probabilities. Like in position auctions, you can allocate them some slots, and then each slot will correspond to certain probability of click-through rate, and only certain vectors of probabilities will be feasible. So you can imagine some space of possible vectors of probabilities. So this is called general environments. Actually, they call like general downward closed permutation environments, and like a good example of them is this position auctions. So quite important setting. All right. So I haven't talked about benchmarks. So for these settings, people have been considering the most standard one is this one, F2, for unlimited supply and online case. So this is best revenue you can get with a uniform pricing. So imagine you set the same price for everyone, and then buyers with a value above this price will buy. So your revenue will be I times VI. But you see, there is this technical condition that there must be at least 2 buyers. So this is because just imagine that if there is one buyer with value V1, there is no way to sell item to him and get his entire value or even constant fraction. So there is no constant approximation, constant competitive auction just for one buyer. So that's why there is this technical assumption to get some interesting results. So for limited supply and position auctions, people consider some kind of generalization of this F2 benchmark. This is called envy-free optimal revenue, E4 for short, where we again need to do this to bring down the highest value guy. So basically, the way people do it is by trimming the vector, taking the highest value guy and bringing him to the second highest. And also, since the problem might be like within some feasible region, we consider this envy-free optimal revenue allocation achieved in some feasible allocation. So I'm not going to describe it in full details, but like that's not going to be super important for the talk. But just to give you some sense of it, in the limited supply case, there is kind of a simple way to bound this benchmark between F2, taken for the highest k values. So you have this inequality. All right, so this was the problem. Okay, so this setting was around for like roughly 15 years. People have done quite a lot of research around it. So let me just describe some latest things. So there was a work by Goldberg, Hartline, Carlin, and Sachs about unlimited supply auctions. So they gave a lower bound of 2.42 against F2. And actually, they conjectured that this should be tight, so they constructed some worst-case distribution and calculated the value for this distribution of inputs. And for limited supply case, Devanur and Hartline gave this two-factor reduction from unlimited supply to limited supply case. And this reduction is super simple. Remember this inequality on NV3 benchmark. It's just at most two times F2 benchmark. So this is essentially the proof. So for online setting, Katsoupias and Pirakos gave two-factor reduction from offline problem to online. And for downward closed environments, High and Hartline had very clever mechanism, and they showed that it's 11 competitive, and then Nikhil came and made it much more complicated. So that's this kind of quite elaborated version of High and Hartline mechanism, but with better competitive ratio, 7.5. Okay, so basically talking about our results, just want to emphasize that this simple idea of looking at the class of benchmarks, as opposed to studying very particular benchmark, give us a fairly long ride. So it really helped us to get improvements over all these things. So for unlimited supply case, kind of the most important step in the proof was the following thing. So for the family of all monotone benchmarks, so imagine that somebody tells you any function that is just monotone, and you want to answer the question, what is the competitive ratio with respect to this benchmark? Then it turns out that you don't need to look at all possible worst-case distributions that you might imagine trying if you want to use like minimax principle, but instead do much more narrow search within some kind of small class of worst-case distributions. So basically, that was kind of very general statement that doesn't give you precise numbers. But basically, given this step, we actually managed to show that for F2, you get this tight constant 2.42. And actually, the analysis extends to actually a variety of benchmarks. So you can do it not only with respect to F2, but actually some family of benchmarks if you want to. So that was quite helpful idea there. So for the limited supply case, again, this idea actually gave us improvement from factor 2 to this beta plus 1. And given that beta is actually the best thing we can get is this 2.42 is kind of significant improvement. And actually, I will show it. The argument is super simple. So for the online setting, so kind of very similar idea just gives you beta plus 2 improvement over 2 beta. And actually, you can do even better if you kind of exploit this idea further, because basically, here the benchmark you use in offline world is the same as you use in online world. But if you use different benchmark in offline world, you can actually improve this constant even further. So actually, it's very helpful to switch gears, in offline setting compared to online settings. So use different benchmarks. And finally, so for downward closed environments, we actually also improved this constant to 6.51. But what is more important, that our mechanism is kind of much simpler than the previous best known one. So it's essentially the original Hind hardline mechanism with some bit different tuning of parameters plus single item weaker auction. So it's essentially as hard as this one. So, okay, right. Okay, so now I want to move to Blackboard. Actually, yeah, okay, so Whiteboard, and as we say in Singapore, also can. So, all right. Oh. So imagine that we have two benchmarks. Let's say we have benchmark F1 is a benchmark with competitive ratio lambda 1. And let's say F2 is another benchmark with competitive ratio lambda 2. So there is a mechanism or like auction or algorithm with competitive ratio lambda 1, and there is algorithm auction or whatever with competitive ratio lambda 2. So what you can say about their sum? So if your benchmark is the sum of two, so what do you think? What would be your guess?
Take the average, do half.
Max?
Well, max is impossible because imagine that F1 is equal to F2, then your ratio should be basically it should increase by factor 2, right? So if you multiply your benchmark by 2, it should increase by 2. So, well, okay, so the answer is actually the sum. And the proof is just one line. It's super simple. So what do you do? So imagine that here we have algorithm A1, here we have algorithm A2. What do? You take on this combination of A1 and A2 with the following weights. Let's call it input. And because this guy is lambda 1 competitive to F1, so we can substitute this with F1, right? So it's at least. And this guy is at least F2 of I. So we get that this entire sum is at least F1 of I plus F2 of I over lambda 1 plus lambda 2.
Would you need to know lambda 1, lambda 2 implement this?
Yes, well, of course, but not precisely. So if you have estimates, you can get this estimate, right? In any case, there is this kind of lemma, super simple, and only it gives you something, for limited supply case. So, okay, let me show you. Does it work? So, well, I'm just avoiding the definition of E42. But basically, for limited supply case, it's really easy to show that it's at most F2 of, let's say, this Vk plus k times Vk plus 1, where we just order guys in this way. So there is this upper bound, and certainly, at least you can claim that Jason knew it, so it's no surprising fact for him. Because for limited supply case, actually there is a quite simple description of this saying. You essentially need to take a revenue curve and basically take a convex envelope of it, and then take value at k. And then this statement is just some simple fact about like single parameter convex function. This is it, so nothing fancy. But once you're here, you see you already can get this improvement because you can say, well, look, let's say that this is my benchmark 1, and let's say this is my benchmark 2. So if this is your first benchmark, well, you get immediately competitive ratio of beta. But if this is your second benchmark, well, you can run simple BCG mechanism with k plus 1 items. You allocate k items. So this is feasible with your number of items. So you can do it. And the competitive ratio is just 1, right? So basically you get beta plus 1 right away. So it's kind of very simple improvement. And what is surprising, like different groups of people work on this and they, missing this simple idea. I'm sure that, this lemma was quite well known to, people doing, yeah, well, I mean, competitive analysis. It's super simple. But basically, I think what was missing is this philosophical point of like moving from single benchmark to variety of them. So, okay. Oh. So, okay. How do I? Right. Actually, I'm almost done, so just have the last slide. Oh yeah, right. Now it's good to erase. So in England, we have this good system. You put this green saying, so that it's good to erase, or you put red saying that says do not erase. There is something super important. Okay, so there are, I think, a few philosophical points that are good to discuss here. So by and large, we do not study these classes of benchmarks. In this particular problem, that was quite useful, helpful, super easy to do. So maybe we should be doing it more often. And like here are some points that I see that are good generally for doing this more kind of general problem. It's like, imagine that you want to do some kind of applications, or like you want to approach some managers and say, well, look, I have this result, Then it's good to have more flexibility, like saying that, well, look, I can handle not only this problem, but maybe something, around it. So generally, doing it for a class of benchmarks gives you some kind of more of description power. And like, as an example, this is digital goods auctions world. Well, it's of course good that we can handle this F2 benchmark, but imagine that we are approached like certain people. They have, well, they might say, well, look, you have this 2.42 approximation, but maybe my market is big, like, middle size or large, and I can almost for sure say that there will be at least 10 good bidders, like high-value buyers. Then, maybe it's a good idea to switch benchmarks, and actually you might be able to show much better, competitive ratio, and that's a much better, selling pitch. So another thing is more theoretical nature. So imagine that you want to do this kind of reduction. So you study a simple setting, but like you want to use these results for another more general one or related. And well, then it's kind of easier to adopt, if you have these general results. And actually, that was already like a good example for this offline and online business. Okay, I should stop very soon. So, and also, the last but not the least, it's very helpful for even improving results, because even if you care about very particular problem, about very particular benchmark, then maybe you can decompose it and get better results. And this last point actually leads to another question. Maybe we can develop better theoretical tools, like providing more general techniques for getting these general statements about composition of benchmarks. Okay, and actually quite interested in this last question, kind of broad philosophical question. Like, given any setting, how we would vary the benchmarks? That's, I think, quite interesting, and probably we should look at variety of them. Okay, so thank you.